that I haven't said anything about it. And also, it's not even necessarily geometric. It's not necessarily true that this is geometric. It's just some generic power series centered at 0 for right now. And my question is, what is P of 0? Regardless of what kind of coefficients we see here, P of 0 will be, of course, C0. Good job. What about P prime of x? Did you see that question coming? Let's ask that question first. What is P prime of x? C1, I hear you say, plus 2C2x plus 3C3x squared, etc. So what's P prime of 0? C1. Didn't you just say that P prime of x is C1 plus 2C2x plus 3C3x squared? That is a whole bunch of things that have an x in them. Therefore, everything drops out and you get P prime of 0 equals C1. Interesting observation. Right? What do you think I'm going to ask next? What do you think P double prime looks like? What's that going to be? You've got P prime in front of you right now, so it's not C2. It's 2C2 plus 6C3x plus 12C4x squared, etc. Again, who cares though? A bunch of things that have an x in them. When you plug in 0, you might be wondering why I'm asking you to plug in 0 to the C2. You get 2C2. Okay. Can we ask about the third derivative, just for fun? What would the third derivative be? 6C3 plus some stuff. Therefore, P triple prime of 0 is 6C3. And the reason we want to just highlight this is that, remember, maybe our goal, maybe we can come out and said what our goal is, but for some arbitrary function that isn't geometric, we'd maybe like to come up with a power series representation. That is, the power series representation amounts to you figuring out what all these coefficients are. Do you agree? Like if you can tell me what all the C0 through Cn are, then you have the power series representation. If you can tell me the coefficients, that's all it takes. And if you have the original function in your possession, this might start to suggest a way that we can say what the coefficients are. Maybe you're not seeing it yet. But we'd like, in the end, to figure out what C0 is, and what C1 is, and what C2 is, etc. Because if we can do that, then we have the power series representation. So let's make this really explicit. I'm going to solve for each of these coefficients. I'm just writing what we had a second ago up here. I just copied it from the previous slide. Do you agree where that came from? This is not, again, let's just be clear. This is not, where are we? We're really broad right now. We're talking about any function, any power series. We're not talking about geometric. We're not talking about a particular kind of series. We're talking about any series representation, right? This is true for that situation. So what's C0? Well, it's just P of 0, right? Like if you want to know the very first coefficient slash constant term, it's just you plugging 0 into the function. So if you have access to the original function, just plug 0 in and you'll get the first constant term. We're doing really well. We need the rest of the series, but we got the first term. Okay. What's the second term? That's not too bad either. What would you do if I handed you the function, not the power series? You might take the derivative and plug in 0, and that would give you the coefficient on the first term. Right? So I'm going to write this way. F prime of 0 is the answer, right? You want the coefficient on the linear term. It's the derivative at the center. In this case, the center is 0. So you take the derivative, evaluate at 0, you get the coefficient on x in your power series. Yeah, sure. Okay, so remember, this is the power series we're talking about. What's P prime of x? That's right, it's this. And what's P prime of 0, or F prime of 0? It's C1. It's the coefficient on the linear term right there. So is that good enough to prove to you that that's where that came from? So if someone asks you the opposite question, that is, I have a function but I don't know the power series representation, what is C1? You can come at it from the other direction. You can say, well, I know the derivative of my function at 0. Oh, that is C1.
So if you're getting the later coefficients, you don't define.
Well, yeah, we haven't talked about those. Those are a little trickier. It's not maybe quite as obvious. I think I know what C0 is. It's me plugging 0 into the function. I think I know what C1 is. It's me plugging 0 into the derivative. C2 is maybe not quite as tricky. You have to do what? It's me plugging 0 into the second derivative, but then also dividing by 2, right? And what about C3? C3 will be us plugging 0 into the third derivative of our function and dividing by 6. What about the fourth derivative? What do we do with C4 if we want C4? We have to divide by, think about what's happening on this last slide here too. Every time we did this, what do we do as the coefficient comes down? We're multiplying by, we keep multiplying by 1 and then by 2 and then by 3 when we take these derivatives. That should remind you of something. I've tried to make it obvious in these first 3. What's in the denominator? In general, what's p, the nth derivative of 0 equals what times Cn? How do we find Cn in general? The nth term of our polynomial. I think it's me taking the nth derivative and evaluating it at 0, but then dividing by n factorial. Okay, so this is a pretty powerful result that we just are talking about. Like, if you have the function, any function, and you want the coefficient in the power series, the nth terms, coefficients, we've just, from pretty simple, again, this is applied generally to any function at all that has n derivatives. Take the nth derivative and divide by n factorial. It gives you the coefficient on the nth term. Boom. And remember, if we have possession of all the coefficients, we have a way of getting every coefficient, then we have the power series in our possession. Do you see where we're going with this? I mean, the thing that motivates our discussion today is, hey, it's been really cool that we've been able to come up with power series representations for a handful of functions that feel geometric, or ones that if we take the derivative are geometric, or if we take the integral are geometric. We have these tricks. The bigger question would be like, can we do this with any function? Can we take like sine x and find a power series for it? Can we take e to the x and find a power series representation for it? Clearly that doesn't have a geometric form, and yet can we still do that? And the answer is like, yeah, we can do all of those things. If we have the derivatives, if we can take n derivatives of something, then we can find the power series. And that's what we're about to do soon here, yeah.
That's a p the n of 0, right?
Yeah.
0.
Sorry. Yeah, it's the nth derivative evaluated at 0. That's what p in parentheses n means. It's not like, does that make sense? Once we get higher than 3 derivatives, we stop doing primes, right? So it's like n primes. We just are not interested in writing after about 3. Now finally a need arises in our lives to take a lot of derivatives. Like that wasn't, we haven't really discussed like anything past the 3rd or 4th derivative because like it hasn't really mattered to us. But now we're interested in taking like an infinite number of derivatives is actually what we're interested in doing. So this result is given credit to by Taylor, but Brooke Taylor is his name. But I don't think he's the one that actually first said it. We have something else called Taylor's theorem that we'll talk about later too, which I think he's maybe more credited for. I have to think hard about what the history on this is. Notice this is the result we just talked about. Now more generally stated for the center being not 0 but a, right? Same thing applies though if we're centered at a. It's just instead of x and x squared, etc., we have x minus a. In the very special case we were just talking about where the center is 0, we call that something called a Maclaurin series. Everybody wants some credit for something. Okay. So this is the big like aha right here that we just talked about on the last slide. If a is 0, if the center is 0, then it's it's the nth derivative of f evaluated at 0 over n factorial. That's what we just talked about on the last slide. But if it's centered somewhere else, neat. It's whatever the center is. keep in mind what we're looking at too, because there's n's, there's an infinity, there's an a and an f. What is this a function of? It's still a function of x, let's just be clear, right? You plug in an x value, I give you back a y value. That's still what this is, this big nasty thing. So sometimes we might call this, on the previous slides we called this Cn, the coefficient on the nth term. And now we can actually come out and say what it is. Powerful, beautiful, wonderful, isn't it? For any function that has, any function we can keep taking derivatives of, we've got it. It's a beautiful thing. And then like on the first slide, we might call the partial sum, P5, for example, in the warm-up, we might call the Taylor polynomial of order 5 or whatever. There's a lot to see on this slide, and this is like the big result, and everything else comes from us realizing this. So take a minute to absorb it and ask questions about the notation if you need to. Yeah, Elizabeth. So let's just make sure you understand. The first line up above is exactly the same as the second line down below, just more compactly written. So what is this? What does this give you? This gives you a power series for any function you like that has an infinite number of derivatives, right? Now we still have to talk about convert. There's this whole discussion still about convergence, like when do things converge? And we'll have to. That's like a big part of this unit too. But isn't it cool that for any function f, and we'll do this in a minute for a couple different functions, that we are going to be able to write out the power series for any function by taking its derivatives and writing out like this. I think that's what we're doing here. We're going to come up with a polynomial for any function. You give me like a exponential function, and I'm going to write you a polynomial that represents it. The answer is yes. What? Yeah. What about a rational function? Like, can I do that too? Yeah. Any function that is got derivatives everywhere. We're going to continue. We're going to be able to come up with a series representation. And though it's maybe not as powerful right now, we're going to start to see the power soon. It's polynomials we know a lot about. Yeah. Polynomials we know a lot about. Don't we really like polynomials? So if you can turn some exotic function into a polynomial, like for math purposes, that turns out to be very useful to us, right? If everything in the entire world is a polynomial, awesome, right? And that's basically what we've just realized today, is that like everything in the world that's smooth enough is a polynomial. Yeah.
So given the series of terms and it has to find f, does that mean we're going to integrate it n times?
I don't think you'll be very often asked, except in the geometric context, I give you the function, the power series representation, and you come up with a function from that necessarily.
But is that because most functions, like polynomials, don't have infinite derivatives, right? Like they just go to 0.
Well, no, they would. It's just the Taylor series for any polynomial will be the polynomial, and every term after that, C, like if it's a 6th degree polynomial, C7 and greater will be 0. So that is the Taylor polynomial. Yep. Yeah.
Isn't, you said it has to be drivable,
Yeah, it has to have, this has to be well defined, right? Like, this doesn't make sense at all if there isn't like a 7th derivative.
What if it's from like a set values where it matters?
Yeah, for sure. For sure. We have to think about where this even matters. So we have to find a place where it matters. And even then, even if there are an infinite number of derivatives, it still might not converge for all values. So we still have that huge discussion to have. Okay. By the way, here are 2 pictures of these guys. Don't you want a wig like that? Okay.
Not really, no.
No? Okay, well. There's another Taylor.
That Taylor's bad.
What?
We're going to learn all these Taylor series here eventually. All right. So let's construct a power series for 6 over 1 minus x. And let's just keep in mind that we have a really simple way of doing that we got earlier. And hopefully it confirms our result. Like we already know the answer to this because we did it in the warm-up today. Isn't this the same one we did in the warm-up today? So like we can even write it out. It's 6 plus 6x plus 6x squared plus etc., right? So let's see if the thing we just said really does work here. Okay, what do we need in order to do this? We need f of, well, we'll write f of x down, but what we need is f of 0 and f prime of x and f prime evaluated at 0, etc., right? We need a bunch of derivatives evaluated at 0. So we'll just do a couple for now and see if we can notice any patterns. Oops. Okay, so the function itself is 6 over 1 minus x. Plug in 0, we'll have that ready to go. We're doing a first. Center at 0. Go ahead and plug in 0. What do you get? 6. And in fact, that is the first term, right? So here we go. We'll write it out here. We'll write p of x, but I don't mind just writing f of x. We can be, it's the same thing. 6 plus something. I don't know yet. I haven't thought about it yet. What's the derivative of this? This is 6 times 1 minus x to the negative first. So it'll be negative 6 times 1 minus x to the negative second, but then times negative 1 by the chain rule. So it actually comes out really nice, the fact that that happened. It turns out that the derivative is just that. Do you like that? Like the fact that there was a negative x in there made that nice. If it was a positive x, we would actually get alternating signs, wouldn't we? Check the arithmetic there. So what's the coefficient here? It's still 6. This is not a very interesting first example. I just want to prove that we do still get the same geometric series representation that we had in the warm-up. So I think I know the next one. It's 6x, right? It's the nth derivative evaluated at 0 divided by n factorial, which is in this case still just 1 factorial. So 6 divided by, okay. Now it's getting a little more interesting now. This is 6 times 1 minus x to the negative second. So what do we have? Negative 12 times 1 minus x to the negative third. But then again, times negative 1 by the chain rule. So we get 12 over 1 minus x to the third. So f double prime of 0 is 12. Okay, you might be like, uh-oh, something's happening. But that's okay, because what are we doing? 12, it's the nth derivative evaluated, in this case, the second derivative evaluated at 0, divided by 2 factorial. So in the end, like I said, this maybe isn't the most exciting first example, because we already knew the answer, and we're getting it now. Of course, we get 6 again. Okay. What about the third derivative? Let's do one more before we like kind of convince ourselves that this is going to keep happening. What do we get here? What's here? Yeah, 36 over 1 minus x to the fourth. And f triple prime then, evaluated at 0, is 36. So that'll be 36 over, it's the third derivative evaluated at 0, that's 36, divided by 3 factorial, right? So, what do you get? You get 6 again. Again, this is a pretty boring first series. It's not this nice thing will not always happen. We'll get very interesting numbers usually on all these coefficients. Promise. But for this example, we already knew this was going to happen because isn't this what we got in the warm-up? 6 plus 6x plus 6x squared plus, it's just geometric. First term 6, common ratio x. So we didn't have to do this process, and in fact, I encourage you to not do this process if you can avoid it. Because in general, this wasn't too bad, taking 3 derivatives, for example. But in general, it's not necessarily easy. In fact, in the homework tonight, just taking a couple derivatives, you're going to be like, oh, because some of them have like, even if it's just something simple like x sine x, right? Like suddenly you have a product rule. The first one's not bad. And then the second one's like a product rule with a product rule in it, and sometimes they get really nasty really quick, okay? So I just want to warn you that like, this is not fun. If you can avoid this process, if you notice this is geometric, please don't do it the way we just did it. We're just mainly like trying to make a point that this works, okay? So this is the answer to A, and the answer to B is what? Can we do it at x equals negative 2? What is it going to be? It's still the same coefficients, right? Except we're evaluating these at negative 2 instead. So we have to like think a little harder about this here. Sorry, that's not 6 anymore. What do these come out to if we Maybe I should have done this on another slide here. Maybe I will. So f of negative 2 is what? Let's do negative 2 now. Is it 2? And f double prime, excuse me, f prime of negative 2. Compute these things. F double prime of negative 2. F double prime, triple prime of negative 2. So f prime of negative 2 is 6 over 3, 6 over 9. Yeah, which is 2/3, someone said, I heard you say. F double prime, plugged in negative 2, you get 12 over 27. 36 over 81. Okay, and you can simplify those too if you like. Actually, all of them can be simplified. What's that? 4 ninths. That's also 4 ninths. Yeah. Okay. So let's write this out. It's 2 times nothing. That's the first coefficient. Plus 2/3 times, not x, but x minus negative 2, or x plus 2, right? Plus 4 ninths divided by 2. So it'll be, here, I'll write that first. 4 ninths divided by 2 factorial times x plus 2 squared. So that'll be 4 over 18, or you could simplify that if you like, or 2 over 9, I guess I should write, right? We have one more term we can throw on there too. It's 4 ninths divided by 3 factorial times x plus 2 to the third, and we have more terms if we want them. So what does that come out to? Is that 2/27 times x plus 3, x plus 2 to the third? How's this working? Maybe you can even just look at this and see what those terms are. Can we write out the power series, represent the actual summation notation for this? It's n equals 0 to infinity. I like the x plus 2 to the n. What goes out here? How about 2 over something? It looks like just 3 to the n on the bottom. Does that work? It's actually still geometric, isn't it? I have another way of maybe having come up with that too, though. Maybe I can convince myself of this. Can I rewrite this as something centered at 2 instead, a negative 2 instead? That is, could I rewrite this as something like this? Maybe, yeah, I'd really like this to be an x plus 2 instead here. How could I make that happen? I want it to be an x plus 2. What do I need here? I'd like to see that somewhere in there. And then give me the right constant to put here. What do we require here? A 3, right? Is that the same thing? Just let's check my arithmetic there. Is that the same thing? Yeah, it is. I didn't change anything, just to be clear. And then, what if I divide everything by 3? Up top I get 2 over 1 minus 1/3 x plus 2. Are you seeing it now?
Yes.
This is geometric with first term 2 and common ratio 1/3 x plus 2. You see it? So you could have maybe come up with a different, and that's interesting. It converges actually for a larger range when we center it around 2, with negative 2. So there's some interesting things that we can do here, right? So, whatever. So, fun stuff. That's the same problem. All right. Let's do sine x. It's a good one to do because sine x is actually something that's not too bad to take a whole bunch of derivatives of. I'll give you a hint. Finding the power series representation for e to the x is also not too bad, right? Because I know how to take infinite numbers of derivatives of these things without too much trouble. So we're definitely going to need f of x equals sine x. And f prime of x we're going to need, that's cosine x. F double prime, we're having fun now. F triple prime,
But you just assume it's centered at 0.
we haven't actually made that decision yet. But let's do it at 0 first, and then we can maybe change our. 0 is a good low-hanging fruit. I like 0 a lot. But we can do it at other places too. But we will need all these derivatives no matter how you slice it. Triple prime, negative cosine. Let's keep going. F, the fourth derivative. Sine x again. And then the fifth derivative. Cosine, I think I'm getting the idea. Okay. And then, yeah, because it doesn't say otherwise, let's center it at 0 for now, and unless someone comes along and tells us that they want to center it somewhere else. F of 0 is 0. By the way, I probably wouldn't want to center it at 1, Michael. If I wanted to center it somewhere else, I'd probably center it at something that I know the sine or cosine of. F prime of 0 is 1. F double prime is 0. F triple prime, fourth derivative. Do you get the pattern here? Fifth derivative. These numbers are very nice, aren't they? That's great. Okay. So I think I'm ready to write out the power series representation for this, okay? Power series will be, the first term is 0. The constant term is 0. The second term is plus 1 times x. We're centering at 0 right now. That's our choice right now. We didn't tell us. So how about at x equals 0? And then what? Plus 0 over 1 factorial over 2 factorial times x squared. That's not a very interesting term, but I'm just going to write it there for now. Okay. And then minus 1 over 3 factorial times x to the third, right? Plus 0 over 4 factorial times x to the fourth. What are we seeing happen here? Plus 1 over 5 factorial x to the fifth. Yeah, someone told you to like memorize this at one point in your life, but now we're just we're actually deriving it for ourselves, right? This is just one. So what does this come out to be? What falls out? All the zeros, but what do they correspond to? Yeah, all the even powers. So we have x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus, I didn't write this, but I think I know. Okay. So this is a power series for sine centered at 0. And there are a couple of things you should notice about that, of course. For example, if you just take the first term, it's the linearization, y equals x, right? It's the linear approximation of sine at 0, the small angle approximation. And you get better approximations as you go further down the line. Okay, we're running out of time a little bit here, but there's the nice way to write that. And the other thing we should say too is it's easy to remember because it's all the odd powers, right? Of course the sum of an odd set of powers will give you sine x because sine is an odd function, right? It's got that symmetry, right? The sine function is an odd function. Of course its constituent, its polynomial form should also be odd. Okay. All of that just to say it's the odd powers, right? All right, we have to do maybe 1 or 2 slides tomorrow, but you got the idea. You can do anything now.